Um, so hello, it's good to be here at this conference. I wasn't supposed to be here. I'm only here in lieu of Lionel Mason. The original invitation was for Lionel to talk about this stuff in, I guess, can you see my mouse as well? So, yeah.
Yes.
So to talk about the stuff in these papers, and I don't know, he sort of felt that maybe I would have a different angle on some of this. And so I'm going to talk about many of the things that are in these papers, but some of the things that are in these papers are not in this talk, and some of the things in this talk are not in these papers, and so on. And I'm going to take I don't have a big framework or a big philosophy to advocate. I'm just going to take a very down-to-earth approach to the stuff I want to talk about. And in the spirit of rebuilding the Tower of Babel, I'll hopefully convince you that this is related to however you like to see things. I by the way, thought it was funny, a funny title, because of course in the book of Genesis, when they build the Tower of Babel, it's because of their pride. And as they build it, they never complete it because God strikes them down and scatters them to the four corners of the earth. And that's why everybody speaks with different languages. And so I hope that isn't the outcome for this meeting, and certainly not the outcome of my talk, that God strikes us down and you all retreat into your own different languages. I'm very sort of language omnivorous, so I'm not going to try and be dogmatic about languages. The general background, to go back to zeroth order, like 1970s basics for this whole thing, is of course that when you're doing gauge theory, there's a color decomposition associated with gauge theory. I just want to pause to emphasize one minor thing about that. So it just follows from the Feynman rules when you write down a gauge theory, that when you write it out, it's going to look like this: a sum over trees times of some kinematic thing times a color factor. And color factors, despite the fact that your Feynman diagrams always have higher order contact terms, your color factors are always ultimately sums of these trees, sums of these Lie things. So where does Lie stuff come from in gauge theory? It comes from color factors, and the fact that in gauge theory, we have a Lie algebra that is always sitting there. And then the partial amplitude decomposition comes from expanding these color factors, which are trees, expanding that Lie monomial into a sum of different orderings, or diagrammatically going from cubic diagrams to these sort of like surface diagrams. And this generalizes to absolutely all orders in perturbation theory. It's the insight of Errol Tuft in the mid-70s that you can do this for any order in the genus expansion of a gauge theory, and you always have color factors, cubic diagrams, expand them into surfaces. It's just that the surfaces end up being higher genus. The other background, which is also 1980s for this talk, is the work by Berends-Giele. They wanted to compute Yang-Mills amplitudes at tree level. And the way they did this is by coming up with the most efficient method to compute tree level amplitudes in gauge theory that I think we know. It's pretty hard to beat their method. And what I've written down on the side, and I'll come back to this in a bit, is what happens when you do the Berends-Giele method to compute bijoint scalar amplitudes. But the general idea is that you have one off-shell leg, right? So instead of, you don't compute, you do a recursion for amplitudes with one off-shell leg, and then once you've worked out all the things you want, you put that leg off-shell at the last step. And again, this generalizes to any order in perturbation theory, any genus, any number of traces. It's just that at higher orders, the recursion relations start to involve more than one off-shell leg. So the final bit of 1980s background for this whole subject is KLT, and I'm just going to write it out again. But again, I have a small point to make. I can't emphasize this enough. KLT is very simple. The KLT matrix can be very simply thought of as just the inverse of this other matrix that I've written as T, which is just like the matrix of bijoint scalar amplitudes, this sum over trees, but it's slightly off shell. There's a 1 over kn squared there. And I'm really taking a genuine n-2 factorial by n-2 factorial matrix. I'm just taking the DDM basis, right, where I have orderings here of 2 through n-1. And that n-2 factorial by n-2 factorial matrix, when you are off shell, when kn is not massless, is just an invertible matrix. So if you want to sort of not worry about all of these subtleties of how you write down a formula for the KLT matrix, how you deal with the fact that you have BCJ relations, if you know about that, well, just forget about all that, and it's the inverse of this matrix when you're off shell. And then the KLT relation is anything that looks like this, where you have gauge, and gravity, or gauge-like, gravity-like, or a gauge and fermion QCD, gravity gauge, you know, anything like this of this form is KLT. But originally, of course, KLT was thinking about strings. And originally, I wanted to talk a lot about strings, but I don't think I'm going to have time. So anyway, this is the 1980s background, and the plan for today is to first talk about Berends-Giele, which is more closely related to the stuff that Christian was just talking about in terms of BV and strictification. So I'm going to talk about this cool observation, that really beautiful observation we made with Carlos about how to invert the Berends-Giele relation. And that's a super cool structure. It gives you this Lie algebra that we played a lot with, and that comes up. It's a Lie algebra that comes up in string theory computations. And so I'm going to talk about that Lie algebra, and then talk also about how that Lie algebra relates to finding BCJ numerators, which has some links to the BV stuff. And then, in the spirit of building the Tower of Babel, I'm going to talk about CHY, where many of the same structures arise. But CHY is a very different world, because people have their own sort of industries just within the CHY world. And so by going between these two worlds, maybe we'll see that a bit different, but there are some a bit more related than you might think, but there are some, it is, well, we'll see. And we'll see that for NLSM, you go this way and you go this way and you find the same things. And I'll put some explicit formulas up and so on. And then I'll talk about strings and the perturbation series only at the end, because I don't have time, but I also don't feel like I don't have results, so I don't want to waste your time on speculations. So for the first stuff, we're just in super old school Berends-Giele world. And what is summarized on this slide is how you would compute bijoint scalar amplitudes if you were Berends and Giele. And the way you do it is you start with, I might have to, I don't know. Do you guys also see these little like thumbnails?
No thumbnails.
You don't see the thumbnails. Okay. So the way you seed the recursion is you say TI, where I is just one of, 1, 2, or 3, or 4, or whatever, is just that first element of the, either you can think of I as just as a arbitrary non-commuting variable, or you can think of it as actually taking values in the adjoint representation. Doesn't really matter. And then the way you do it is in bijoint scalar, you just have one Feynman vertex, which is the cubic vertex, And the way the cubic, and what is the Feynman rule associated with cubic vertex? It just says FABC, where ABC are the, if you're a physicist, it's FABC sub-adjoint or whatever, which just means take the commutator of this lambda with this lambda. And so I've just written that commutator there. You can think of it as an abstract commutator or a commutator in the adjoint representation. And in the usual Berends-Giele way, you swap out a Feynman rule for, you have your one off-shell leg, and it comes down and meets a cubic vertex, which goes off in 2 directions. And this gives you a recursion for the currents. And it's, which is this formula written here, where SA is the Mandelstam. So this is the pole associated to the momentum of all the particles in the word A. So if A was 1 through n-1, this would be 1 over the square of the sum of momenta k1 through n-1. So the key thing that we observed was that you can invert. So this expresses the big current with the long word as a sum of these terms, right? How would you write one of these terms in terms of these big currents? Well, there's a way to do it, which is this line, where curly bracket B comma C is this wacky operation, which I've written down here in full, not to scare you exactly, but just for the record, I've written it down in full. And it's really, you should think of it as a bracket. It's anti-symmetric in a sense that I'll explain in a second. And it's given by the super explicit formula, which looks unwieldy until you realize that you recognize shit like this from elsewhere. You know, you've got this, so this sign is the shuffle sign. So like 1 shuffle 2 is 1 2 plus 2 1. It's the way of rearranging the letters without changing the order within the word. So we've seen the shuffle sign before, and this tilde is about reversing the ordering of B2. And this thing, if you just ignore, I can't remember if, does this still work when I do that?
Yes.
Yeah. It totally I only worked out how to do that 1 year into the pandemic. So I couldn't, it really changed my my Zoom work experience to be able to doodle like that. So this thing, B1 shuffle tilde I, that's the same as the combination of orderings that appears in the KK relations. And so if you just sort of focused on this side, that's just like a KK relation sum. And then this side is also just like a KK relation sum. So this is closely related to the KK relations, which I'll come back into a sec. And then the other thing to notice is that this bracket has, it has these Mandelstams, Sij, so Ki plus Kj squared, and it's of linear order in the Mandelstams. So whenever you see a pair of curly brackets, you know that's a power of 1 power of Mandelstams. So I just said that Kleist-Quiff is related to related to like shuffles and stuff, and also, well, I can't remember what I just said, but the thing I want to emphasize on, I didn't write it down, but so the thing I want to emphasize just in this corner for a sec is that what I mean by the approx, I've written AIB is approx I A tilde shuffle B. That's an identity just in non-commuting words. If the approx means that the difference between the left-hand side and the right-hand side is just a sum of total shuffles, right? And one thing that we know about amplitudes and also, which is also satisfied by Berends-Giele currents, is that if we look at this T B shuffle C, that's always identically 0 for T a current or an amplitude. So total shuffles get killed by the amplitudes. And this is literally because of primordial reasons having to do with the fact that all gauge theories can be written like A alpha, C alpha. It's super primordial. It has no real, it's just foundational to the whole subject going back to the 70s, because shuffles are killed when contracted into Lie monomials. That's just an algebra fact. And so this KK relation, T B shuffle C is 0, is just super foundational. And so if shuffles get cancelled, then you have relations like this, because this equals that up to a sum of shuffles. Anyway, so that's just a kind of just a rant. But the cool thing about this solution to inverting Berends-Giele is that this bracket operation you discover is then a Lie bracket. But it's a Lie bracket on the space of orderings considered up to shuffle. That's the right space for amplitudes and for Berends-Giele currents, because of my rant just concluded. And so it's anti-symmetric up to shuffle, right? So 1,2 is S1212 and 2,1 is S1221. And those are not equal as expressions, but they differ only by a shuffle. And likewise, the Jacobi relation is satisfied by the curly bracket. And so you have a weird Lie algebra on the space of orderings up to shuffles, tensor the space of Mandelstam variables thought of as a formal ring. And so yeah, you might be surprised if you discover this, if you start from this point of view. The cool thing about it as well is, I mean, it's cool that it's a Lie algebra, but the reason why we actually cared about it was because it just immediately gives you everything you want to know about the Klt matrix. Because if you think about nesting these curly brackets, then if you nest them, eventually you're going to get back down to the start of the recursion where Ti is just equal to lambda I. And so if curly bracket alpha curly bracket means sort of a bunch of nested curly brackets like that, you whack that into the Berends-Giele current, what you get back out is just a pure color factor. And so once you know about the S bracket, you have this inverse operation, which takes a color factor monomial or Lie monomial and gives you back a sum of orderings that inverts the T, that inverts the Berends-Giele current. If you think of the Berends-Giele current as a map from orderings to something with values in these Lie monomials of color generators. And so what I've just written at the bottom is how that relates to the conventional wisdom, because if I expand the map T and the map S in a DDM basis, it literally gives you that thing that I told you at the start, the kind of cheat sheet way of remembering KLT, that that S, this matrix of the matrix elements of this map, is just the inverse matrix of T. And it's super easy to compute everything that you might want to compute. And, you know, Carlos Mafra was interested in a bunch of recursion relations, which also immediately follow from these. And that's why his computer code he uses those recursion relations in his favored code to compute all of the Klt matrices explicitly. Okay, so that was just biadjoint scalar, and inverting Berends-Giele for biadjoint scalar gave rise to this interesting S bracket or curly bracket. More generally, of course, you don't have such an easy time because you have higher order contact terms, like the ones that were just being talked about. And so your Berends-Giele relation looks a lot like this. with like that, where you have each term corresponding to the higher order vertices in the theory. So you can, for instance, with Yang-Mills, the thing that they actually did in the 80s, they just considered the first two terms. If you like, you can take this relation, and by extending the Berends-Giele current to have some higher order extended currents, you can collapse this formula into a formula that looks like this one, which I think must be the same as strictification, except that it's not unique. So you can do this in many, many ways, and it feels like strictification because you then have one cubic thing. But there's, I just feel icky about it because, there's nothing super unique about how you set this up, as far as I can tell anyway. Up here, of course, there's nothing super unique about these rules either, as Berends-Giele talk about, because, in order to have your currents, you have to propagate a gauge condition. So in the paper, they probably use Lorenz gauge, and they have to check that their specific rules propagate the Lorenz gauge condition every time you do the recursion, but you could choose some other gauge. And more generally, there's a kind of both gauge and field redefinition freedom, which was also just being talked about. And so, but yeah, if you find a way to write Berends-Giele in this cubic form, it must in some way mean that you've understood what the strictification is, even if I don't feel like when I do this, I've understood whether I've done something unique or not. But maybe that's something that other people on this call understand a lot better and will be able to explain to me later. In any case, so I've written down these two ways of writing down the Berends-Giele thing, and we'll do an example in a sec. And then once you've got your currents, you put them on shell, you remove the last leg, and you get the partial amplitudes. And so maybe I'll just fast forward to an example. So an example of what I was just talking about is where this is Berends-Giele, and I haven't written down the Lorenz gauge rules, but just imagine that they're there. And this is an extended version where you can write the whole recursion in a cubic way. And if you just think about it for a sec, you have to check carefully that this is doing the right thing. But by adding this second Berends-Giele current, this antisymmetric tensor B, you can check that you are in Lorenz gauge reproducing the Lorenz gauge Berends-Giele cubic rule quartic rule with a cubic rule of this form. And maybe I just need to sort of close my eyes and really think hard. It's not super clear to me how this relates to anything you do at the Lagrangian. So I just know that this solves this problem for writing Berends-Giele in this way. It's not super clear to me how it relates to writing down a cubic Lagrangian, though it may do. And also, it's not super useful if you want a BCJ relation, because you move off. You have an antisymmetric bracket here that you get by introducing this B current, but it's not a Jacobi current, even when you impose all the gauge conditions. So you have a quick way of this is a quick way for me with pen and paper to do some computations I might want to do, but this isn't a way to enlighten myself about BCJ. And this is somehow the tension, right? That this is one way that I would sort of wandering around find the tension in the BCJ subject. It's like this. I suppose I, for whatever reason, felt that it was simpler and nicer to write my amplitudes in these BCJ forms. This thing out the front is just a sign, a comma alpha. It's just a sign to keep track of. Well, it just has to be there. But the point is, suppose I wanted to write my amplitude as a thing labeled by a tree over the propagators for that cubic tree. And, you know, just to remind you that this does go back to the early 70s, that's exactly what you would do if you computed the gauge amplitude in the early 70s. It's just that you wouldn't think too hard about the form of A alpha. You would just compute and find out what it is. Whereas with BCJ, we're computing it, finding out what it is, and we're assuming that there's something interesting about this N alpha. And we also don't want to do anything dumb. So we don't want N alpha to be something that has poles in it. We want all the poles to have already sat themselves down in this propagator factor. And so the tension as it appears when I'm stumbling around is that with my curly bracket, which is related to this 10-year-old thing, as I'll say in a sec, I can just write down what the N alpha are. It's just, if you give me a cubic tree, I just write down its monomial, but in terms of Lie brackets instead of in terms of adjoint brackets. And then I just whack it in. And I know that this satisfies Jacobi because the curly bracket is a Lie bracket. And so I have all these Jacobi satisfying numerators. And so I'm happy with that. Except that in general, this has spurious poles. So I get a formula for N alpha that satisfies this, but will in general have spurious poles. On the other hand, I could stare at the gauge fixed Berends-Giele recursion relation rules. I can extend my Berends-Giele bracket for computational sakes. And then again, having done that, it naturally computes the amplitude in this form, because I just take my Berends-Giele bracket and I bracket it according to some Lie monomial or some cubic tree, if you like. And that's great. It has no spurious poles. You can see from this formula, for example, that there's nothing spurious happens. But in general, you might not know whether that's a Lie bracket or not. And this is where the tools of the previous talk must surely be able to help me, even though I haven't worked out how to use them to help me. It feels as if this business about quasi-isomorphisms between Lie infinity algebras is the right sort of thing. It's the right sort of results you would like, because you would like to be able to say, in general, if I start with some Berends-Giele rules, is it possible to find a Lie satisfying cubic Berends-Giele rule? And I'm saying Berends-Giele instead of Feynman rules because the equivalence is a little bit iffy in my head, just because in Berends-Giele there's this stuff about propagating the gauge condition and keeping one leg off shell. Anyway, so here's the tension, and you see that tension in Yang-Mills, because in Yang-Mills you can sure as hell do this first thing and you get some numerators that have spurious poles, and you can sure as hell do the second thing and you get some nice numerators that don't satisfy Jacobi. This slide is saying that my option 1 is the same thing as something you all know, or you might have come across just in the general amplitude C world, because all N of curly bracket alpha is saying is it's because of the way that curly bracket is basically the heart of the KLT kernel. It's just saying use the KLT kernel to get these numerators, which is a age-old trick that people have done. But it's useless because you get spurious poles, so nobody likes it. Except for NLSM, where you get some nice stuff, and that's summarized on this page, some of the nice stuff that you get. So if you put the field equations and choose the gauge conditions in a certain way, which is essentially the way in the paper by Mazera and Skripek but probably also this is sort of widespread knowledge about the NLSM field equations. You can come up with a Berends-Giele recursion, which uses a bracket that is essentially Sophus Lee's Lie bracket. It's exactly just the commutator of two vector fields, and it's the way I like to do it. I have it it's just a central extension of the commutator of two vector fields by an extra scalar. And so you see that this Lie bracket here is just the central extension of the, if you crossed out the second line, the sort of naive Lie bracket for the vector field of the Lie algebra of vector fields. And in momentum space, that's written here. And if you seed the recursion with appropriate amount of gauge fixing with some seed currents, then you end up with a nice BCJ-esque form, numerator over denominator. And then you work out what these numerators are, and they are exactly the numerators that were found by, among other people, I think. I'm not sure the full extent of the literature on this stuff, but on this particular example. But I think one of the first places it appears is Carrasco, Mafra, Schlotterer, where they write their n alphas in terms of these capital N's, and those capital N's are these diagonal entries of the Klt matrix. And you find that by just doing Berends-Giele. So if you wanted to compute NLSM with Berends-Giele, if you do it in this gauge, which is a great gauge to do it in, you find the you find those diagonal KLT entries again. So this is a tension, except when it works, and I only know when it works, and I don't know when it doesn't work, how to rule out that it can't work. And that's why maybe the systematic tools should be applied to this sort of thing. But I'm just talking here at this concrete level about what you can do with formulas. I was gonna say here, this is more or less the end of the first half where I talk about Berends-Giele in an old-fashioned way. And I was gonna say something here about how all of the above, you can throw in fermions, and you can also go to higher orders in perturbation theory, and so much remains the same. But I don't know, if you care about this QCD side, then I probably don't have much to teach you, other than that indeed all of the stuff about Lie monomials restricts nicely onto what happens when you restrict some of the branches in your cubic trees to be fermion lines. And this just goes back to this kind of basic algebra of ribbon graphs, again, a nice old subject, which look like this. And each ribbon graph contributes to a partial amplitude, which is labeled by a diagram that looks like this, which is like the partial amplitude, which is like the disks that label the partial amplitudes of full Yang-Mills theory, except that there are some missing bits. Yeah, so there's no problem if you want to have some missing bits, but let's maybe not talk about that, because I want to move on to the second bit. So the second bit is about M0n, moduli of points on the Riemann sphere, and CHY formulas. CHY formulas were a great boon for the subject for a good period of time, because of all of the new formulas that they led people to find. They're a bit tricky to use, CHY formulas. So in my book, I would rather never use a CHY formula to actually get to the gritty end of the computation. But if you don't actually have to evaluate the CHY formula, they're great, because if you don't have to evaluate them, they're just about rational functions on M0n. and the ring of rational, or on configuration spaces, if you like, and the ring of rational functions on M naught n is this lovely ring. You get all these lovely functions, and the functions satisfy things which make them very easy to compute with. So I'm very happy to sort of do computations that involve rational functions on M naught n. I don't want to evaluate the CHY formula because it's bullshit. You have to solve the scattering equations, which are the set of awful equations, extremely high order. They have a gazillion solutions. You have to sum over the residues. I don't think anyone really wants to do that. But if you can find a CHY formula and manipulate it, then you can still work out the amplitudes, even if you don't evaluate the CHY formula. And that's because you can relate the amplitudes to bijoint scalar. I think that's one of the computational boons of having a CHY formula in your pocket. So on this slide, I summarize some stuff about what I've written down a broken Park-Taylor. The thing that's broken about it is that it doesn't go back to 1 at the end. So it just starts at 1 and goes through to n-1. Those broken functions satisfy the same thing as before, that they're killed by shuffles, which means that they also satisfy the same thing as before, that they this Kleist Kleist-Quiff relation, but just as a statement about these functions. And so you can really think of this broken Park-Taylor thing as something that starts from that same vector space of orderings modulo shuffle relations. It gives you a natural map from that space to the space of rational functions on the configuration space, minus the divisor given by the big diagonal when Zi equals Zj. And the super cool thing is that if you've ever lived in the CHY world, you come across scattering equations. Scattering equations are the differential of the log of the Kobe-Nielsen factor in old style string theory. The Kobe-Nielsen factor is the product of Zij to the Sij. You take d log of that, and you get stuff that looks like Sij over Zij, where Zij is Zi minus Zj. And your general scattering equation looks like this, where I have an ordering A and an ordering B, or just a set A and a set B, if you like, and then and they're disjoint, and for each I in the first set and J in the second set, I put down an Sij of Zij. And then turns out scattering equations as things you can write down in your as functions you can write down on conv n are the curly bracket. So the same curly bracket that we found by inverting BG is here the result of multiplying by scattering equations. So I wrote it down. This is just what I said now in words, that if you take one of these functions and another one and you multiply them together with this thing, then you get the curly bracket. It's super easy to see why that is. It's not particularly deep, but this is the reason why CHY is related to the S bracket and the Berends-Giele problem that I started the talk with. And some of the matrix identities, like these ones, which are really go back to the start of the CHY subject, they're in the first papers about the CHY stuff. These identities are also follow from the S bracket stuff, and I've written out a summary slide of how you do them, and they come from two identities. Essentially, they come from Kirchhoff's theorem, which allows you to compute the determinant as the sum of spanning trees. And they come from this thing I just said before, that the broken Park-Taylors are really functions of, they're really labeled by this vector space, orderings modulo shuffles, which means they satisfy things like this. It's those two identities which allow you to compute the determinants of these matrices. So this matrix A, Sij of Zij, with the diagonals given by minus the sum of the row, If you use Kirchhoff's theorem to evaluate it, you get something like this: product over directed edges in the cubic tree G of the entries of A. And then you use Kleist-Quiff to reorganize them, and you recompute this guy. And this guy, det A, is diagonal of KLT times PT. That should look familiar because that's what we found before for the numerators of NLSM, a very often derived result. And you can derive it in the context of CHY, not by doing Berends-Giele as we did before, but by writing down the CHY formula and then evaluating it. And you evaluate it by computing the determinant with Kirchhoff. And I've also written down this other identity, which was pretty big in one of the, pretty key to one of the original papers in this subject. So just to summarize, this is the avatar of the S bracket in CHY world. And we can again compute the numerators for NLSM. And this slide summarizes what you do when you try and compute the numerators for Yang-Mills, which is a fine exercise. So just to briefly give you a tour of this slide, what I've written here is the 4D general relativity. This is the 4D Einstein, pure Einstein amplitude formula. In the CHY literature, there's a bunch of different papers that give formulas of this form for Einstein, but it more or less goes back to Cacciaso-Skinner, although their formula doesn't look exactly like this. And I've written it out in 4D, where you use spinor helicity. So these lambdas, lambda tildes are spinors in the two representations in 4 dimensions. And you get a measure, an integral measure that looks like this. Again, it's shit if you want to actually compute, because like all CHY formulas, you have to solve all of these delta functions, which is a ridiculous thing to ever do. But if you, the key meaty bit of the formula are the Hodges matrices. Andrew Hodges originally found those matrices when he was computing, doing some explicit computations of the Einstein amplitudes, or gauge amplitude. I forget what his first paper was on, but these are the two Hodges matrices, and they have these scale variables that are implicit in the whole formula in them. And the diagonals are minus the sum of the rows again. And so you can again use Kirchhoff's theorem, the matrix tree theorem, to expand them. And when you expand them, you write the 4D pure Einstein amplitude as a sum over pairs of trees. And so you have integral this measure times IgG prime, where G is a spanning tree of 1 through K if particles 1 through K are plus, and G prime is a spanning tree of the set K plus 1 through N if K plus 1 through N are the particles that are minus. And in general, this gives you a really, and you have 3 factors here: products over edges of the graph, and then a product over the vertices to the power of degree of the vertex. And in general, this gives you a not much better way of computing the answer, because you have to go through the CHY way. But if you expand these products over 1 over Zij, again, using this essentially Kleist-Quiff relation between product over edges of the graph and sum of different orderings, then you get some nice formulas, at least for low MHV degree, because at high MHV degree, you get a real problem coming from messing with the T's. But at low MHV degree, you get something like this, which gives you numerators. it gives you these capital N's, but it also gives you the N alphas, because if you know the capital N's, you know the N alphas. And this is a formula that I guess Berends-Giele Quiff could have written down, because there's this paper by Berends-Giele Quiff where they use KLT plus recursion relations to find formulas for gravity. I've slightly, this is a sort of, this line is kind of a typo in multiple senses, I now realize. So I apologize for that, and maybe ask you just to focus on N equals this. And if you've ever read the BJK paper, you'll see it's not the BJK formula, but it's a little bit like a formula in a paper by Lionel Mason and David Skinner, and their way of getting to the formula for the amplitude was twistorial. So using a more twistorial version than this formula, but of this formula. And so this is like the equivalent of that formula, but in this slightly different, more ambidextrous form. But the point is that, and back then, you know, in 2011 or whenever they published their paper about the BJK formula, nobody cared about finding BCJ numerators, or BCJ did in 2011, but I don't know that they were aware of that as a goal. But you do get, again, you get an N alpha. But if you look at this formula for the numerator, it has some spurious poles in it. And it only has spurious poles involving 2 and 1, which are the singled out variables, singled out by being plus. But it has spurious poles nonetheless. And so unlike what you got when you used CHY in an LSM, Yang-Mills gives you a formula. Jacobi is satisfied, but you have spurious poles in these square brackets. Okay, that's all I wanted to say about how this stuff relates to CHY. And to summarize by looking ahead a little bit, and to say again some of the things I've said before, from the first part of the talk, it would be really good to know if, you know, because I love this super hands-on, I can literally just do it way of computing amplitudes with Berends-Giele. I love my way of being able to do that for NLSM. I love my way of being able to do it for Yang-Mills. But when I do it for Yang-Mills, or indeed any other gauge theory, I can get answers, but I won't get numerators. And I have a bracket there that is not Lie. And so is there a systematic way to sort that out? Go from the Lagrangian to the currents. It's great that all of these methods have been developed for Lagrangians, and I'd really like to know if that just answers on the nose my questions about currents, or whether there needs to be something else done in order to answer the stuff about currents. And then as concerns M0n and the M0n world, there's more connections, I think, between S bracket and a lot of stuff that people have been finding in the M0n world. I didn't talk about string computations. I've written in a little box how the curly bracket can be seen appearing on the right-hand side of what happens when you hit a multi-particle vertex operator labeled by an ordering A with the BRST operator in superstring computations. You find that the curly bracket, you sort of, BRST hits the thing and gives you sort of D curly bracket in the sense of DE, anti-curly bracket. It sort of unbrackets. It's the structure of a co-bracket that's dual to the curly bracket. And so in general, that means, and if you think about Lie algebra cohomology, Lie algebra cohomology is a chain sequence where you hit at each level with the co-bracket, right? If you have a Lie algebra, you have a co-Lie algebra, and so there's a relationship here between computing the BRST cohomology of a string theory and the just bog standard. Everyone knows that BRST cohomology is related to Lie algebra cohomology, but there's a kind of basic Lie algebra with a basic Lie algebra cohomology given by the S bracket Lie algebra and its co-Lie algebra. And that's something that we thought a bit about. I don't yet know how deep I find this, but we've worked out some of those calculations. And then the other thing that I wanted to say about, after M naught n,
we're almost out of time. I'm very sorry about this.
Yeah, this is my final. This is literally the last line. Okay. The other thing that I wanted to say was that string theory would be lame as anything if it was tree level. Tree level string theory is not impressive. But it goes to the whole perturbation series, and when you go to the whole perturbation series, you still get Berends-Giele recursions. It's just that at each step, and it is recursive because at each step you go down in the perturbation series, but you add more and more higher order legs. And so if you care about that sort of thing, this is a schematic page where I invite you to imagine trying to do Berends-Giele for the torus, for example, which would write the torus current in terms of annulus currents with 2 off-shell legs, and so on. And I think that the Klt kinematic story will be so uninteresting and so will be superseded by other considerations if it doesn't continue in an interesting way to this context. But thanks to Tuft, we know that this is a context that makes sense because all of the color factors are labeled by surfaces with boundary, and all of the amplitudes continue to have these color factor expressions in terms of cubic diagrams. So yeah, that's all I wanted to say, and very interested in any thoughts and so on, any help.
Thank you very much for the very nice talk. Questions?
Yes, Christian?
Yeah.
Christian, you're on mute. Oh, sorry.
Sorry, I was clicking on clapping.
Oh, sorry, I'm sorry.
I mean, just a quick comment. The strictification isn't unique either, right? You mentioned you were worried about strictification being unique, but strictification is not unique, right? So there's no contradiction there. And the Berends-Giele relations, as I said, it really follows for any field theory that you can put in the BV formalism, right? There's always a recursive relation that you can formulate. I have to look at your paper more. It seems like you're doing something dual to what I understand, but yeah.
Indeed, yeah, it is sort of dual, and I guess the question is there a risk that if I took like your Feynman rules and then fixed my gauge and started writing down my Berends-Giele recursion in this form, am I going to get a Lie algebra or not? Is I guess my question. And because it's a little bit dual, it feels dangerous to assert that your result would be strong enough to guarantee that this is Lie algebra.
Yeah, I guess you wouldn't get Lie algebra. You would get an L-infinity algebra, right? You wouldn't. Do you see what's going on, Jean-Marc?
Yeah, the Lie algebras involved here are there. If I read through it correctly, weren't those free Lie algebras or something?
Earlier, I was talking about a free Lie algebra. Well, I wasn't talking about the free Lie algebra per se. This bracket is not the free Lie algebra. This is a bracket that's dual to free Lie algebra cross a ring of Mandelstams.
Basically, but whenever you have free Lie algebras, I mean, by causality they're dual to C-infinity algebras, and you know that C-infinity algebra is precisely what
I don't care about free Lie algebras. I care about this Lie algebra. That's not a free Lie algebra.
I see.
That's I care about Berends-Giele because I care about being able to compute an actual thing, which means I care about this bracket, right?
Mm-hmm.
I'm very happy with my S bracket stuff, and free Lie algebras where everything is very simple.
We have also another question by Shruti, right?
Yeah, thanks for the nice talk. I was wondering if you've looked at these papers that study color kinematics in ADS, and basically they have this kind of Berends-Giele type recursion, except they're doing it now not in flat space. I'm wondering if your methods also could extend into that ADS context.
I have no idea about these papers. I haven't even been thinking about numerators until Lionel foisted this talk on me. But that sounds great.
Okay, there are these papers by, just for reference, Cliff Chung, Para Martinez. And
oh, yeah. Yeah, no, I remember Cliff talked about something like that. Yeah. Okay. Yeah, no, I haven't thought about whether that their formulas would strictify in this way.
Mm-hmm. Okay, thanks.
So, okay, thank you very much for the questions and your answers. And I think now it's time to go on with the next speaker. So we have John Joseph Carrasco. He will talk about color dual effective field theory. So.
Hi, I'm going to connect to my iPad if that's okay.